Welcome back, everyone, to today's Explainer. We're about to take an absolutely wild top-down journey. Seriously, we're tracking data from the exact second it gets packaged up in abstract software all the way down into the literal physical wires that connect our entire world. It's going to be a fun one.
So you might be wondering, how does a digital packet actually survive a trip across a physical wire? I mean, think about it. We send data across the globe in milliseconds, right? But bridging that gap between invisible, abstract network layers and chaotic, tangible hardware, well, it requires some incredibly precise engineering.
Okay, let's dive right into this. Here's our roadmap for the day. We're going to start with packaging Ethernet frames, then enter the physical layer, unravel some cable categories and wiring types, and finally, we'll wrap up with fiber optics and power.
All right, part 1, packaging Ethernet frames.
Think of the datalink layer as the networking world's ultimate shipping department. Before a packet ever even touches a wire, this layer builds a protective envelope around it. That's the Ethernet-2 frame. It literally takes the packet handed down from the network layer and securely encapsulates it, tucking it away so it's fully prepared for the crazy physical journey ahead.
Let's actually break down this envelope piece by piece. First up, the preamble and SFD. This is basically an alternating 1-0 pattern that acts kind of like a metronome. It lets receiving devices perfectly sync their internal clocks to the incoming bit stream. Next, you've got your destination and source MAC addresses. These act as the to and from labels, identifying the specific hardware devices. Then comes the type field, which tells us exactly what network layer protocol is hiding inside, like IP or IPv6. After that is the payload itself, the actual 46 to 1,500 byte chunk of data we're trying to send. And finally, the FCS. This runs a really complex math problem called a CRC to mathematically seal the entire frame. If the math doesn't check out when it arrives, bam, the frame is instantly discarded, no questions asked. Remember though, this provides error detection, not error correction.
Moving right along to part 2, entering the physical layer.
You know, once our perfectly framed packet turns into raw electrical pulses, the hardware rules become incredibly unforgiving. To really ground this in reality, let's look at an anecdote from a network consultant who was tracing intermittent outages in this massive aerospace warehouse down in LA. The warehouse workers there were constantly complaining, saying, "Whenever my host stops working, that becomes my most stressful part of the day." And honestly, they're not wrong. When physical layer specs are ignored, hardware fails unpredictably, and it causes massive headaches for literally everyone relying on it.
And this brilliantly illustrates why those strict physical limits matter in the real world. Think about a PC that is connected to a hub 115 meters away, while that extra 15 meters directly violates the 100-meter Ethernet specification for unshielded twisted pair cable. Hosts situated within the proper 90-meter range work flawlessly, but that extra length on the distant PC is exactly what caused it to randomly fail during the absolute worst, most stressful parts of the day.
So, what's the scientific culprit here? It's something called attenuation, which is just the loss of signal strength measured in decibels. Think of it like trying to hear someone whisper from all the way across a really crowded, noisy room. The further a digital electrical signal travels down a copper wire, the weaker and more distorted it gets. Once you push past that 100-meter mark, the signal degrades so much that the receiving device simply cannot read the ones and zeros accurately anymore. It just turns to mush.
Okay, part 3, unraveling Ethernet cabling categories. Now, what's really interesting here is how engineering handles massive jumps in bandwidth over the exact same physical distances. Just compare a Category 5 cable, which maxes out at 100 megabits per second, to a Cat 6A, which pushes a massive 10 gigabits over that very same 100-meter limit. The secret? It's all in the physical twists. Higher quality cables actually pack in way more wire twists per foot. This dramatically reduces what we call crosstalk, basically the unwanted electromagnetic interference between the internal wires sitting right next to each other. Less interference means you can reliably push a whole lot more bandwidth over the exact same physical distance. Pretty clever, right?
Which brings us to part 4, wiring. Specifically, straight, crossed, and rolled. Here's the thing. Just having the right category of cable isn't quite enough. The internal pins actually have to align perfectly for the devices that are communicating. If we look at a standard straight-through cable, you'll notice pins 1, 2, 3, and 6 map directly to those exact same pins on the other side. We typically use this to connect a host to a switch. But if you're hooking up similar devices, like a switch connecting to another switch, you absolutely need a crossover cable. Notice how the transmit pins, 1 and 2, physically cross over to become the receive pins, 3 and 6, on the opposite end. If you don't use a crossover here, the two switches will essentially just yell at each other at the same time and no data will actually be received.
Then, we have the totally unique rolled cable. Check this out. All 8 wires are completely inverted. Pin 1 goes to pin 8, pin 2 goes to pin 7, and so on. But here's the catch. This isn't used for normal Ethernet data at all. Nope, it's specifically used to connect a host's EIATI232 interface directly to a router or switch console port. It's a highly specialized cable built for one purpose, letting you log in and configure the networking hardware itself.
Finally, we arrive at part 5, fiber optics and power. So, what happens when standard copper cabling just totally hits its physical limits? Well, we turn to fiber optics. This is where we transmit data as actual pulses of light at mind-bending speeds through microscopic glass waveguides. Because it's light, it's completely immune to electromagnetic interference. There are 2 major types to know here. First, single-mode fiber. This has a super tiny 9-micron core. It is definitely more expensive, but since it propagates a single, hyper-focused mode of light, it can travel intercontinental distances, literally kilometers, without the signal failing. Multi-mode fiber, on the other hand, has a much larger, looser 50 or 62.5 micron core. This lets multiple light particles bounce down the glass. But because those particles scatter and then have to be reassembled at the receiving end, multi-mode is strictly limited to much shorter network distances.
Now, on the flip side of that, what if we want our standard copper cables to do a little more heavy lifting? What if they could do more than just send data? Enter Power over Ethernet, or PoE. This is an absolute game changer. It cleverly transmits electrical power right alongside your data, using those exact same standard twisted pair cables. Governed by IEEE standards like A2.3AF and A23.3AT, PoE is totally ideal for powering things like IP phones, Wi-Fi access points, and security cameras. It's brilliant because it completely eliminates the need for having licensed electricians come out and install costly separate electrical wiring. You literally just plug in your Ethernet cable and boom, your device powers up and connects to the network all at exactly the same time.
As we wrap up today, I want to leave you with a thought. As Ethernet speeds push to 10 gigabits per second, and honestly way beyond that, will copper eventually hit a hard physical limit, or will clever engineering somehow find a way to keep twisted pair cables alive forever? It's definitely a provocative question when you think about the future of physical media. Thank you so much for joining me in this explainer. I really hope this journey gave you a much deeper understanding of exactly how our data travels, from abstract software packaging all the way down into those physical wires. Catch you next time.